For anyone who runs or, even just walks regularly, there's this term that pops up, running economy.
Mm-hmm.
And it seems maybe more critical than just raw speed or endurance. It's about efficiency, right? How your body uses energy.
Exactly. Your body's fuel economy.
But what if the way we've been measuring that miles per gallon for our bodies hasn't quite been right?
That's the core question, isn't it?
Today, we're diving deep into a really fascinating new study. It seems to challenge some long-held ideas about how we quantify running economy.
It really does.
It feels like a shortcut to understanding the cutting edge of sports science and, how it might impact training, performance, maybe even just how you think about your own movement.
Indeed. This deep dive focuses on some pretty groundbreaking research. It's published in the Journal of Sports Science and Medicine just this year, 2025.
Okay.
The article is titled, Quantifying Running Economy in Amateur Runners, Evaluating VO2 and Energy Cost with Model-Based Normalization.
Got it. Who's behind this work?
It's authored by Xiuli, Zhang, and Zhaowei. They're from the University of Macau and also South China Normal University.
Right.
And what's really compelling, I think, is how rigorously they re-examined these common methods we use for assessing running economy.
Mm-hmm.
And they're proposing some, significant improvements, better ways to make accurate comparisons between individuals.
Okay, let's unpack this then. We should explore why maybe the traditional ways of measuring running economy might be a bit misleading.
Yeah.
Discover what this potentially more precise way is,
Mm-hmm.
and maybe even touch on what it means for, say, differences between male and female runners. Sounds like we're peeling back some layers here.
Definitely. It gets to the fundamentals.
So maybe let's start right there. Running economy, RE. You said fuel economy. Why is it such a big deal for runners, from the weekend jogger to the serious athlete?
It's a great starting point. Simply put, RE is defined as the metabolic consumption, how much energy you're burning at a given steady submaximal speed.
Okay. Submaximal, so not sprinting.
Exactly. Think comfortable cruising pace, or maybe marathon pace. And it's crucial because it's often a better predictor of endurance performance than even VO2 max alone, especially when you're comparing runners who are otherwise quite similar.
Really? Better than VO2 max?
In many cases, yes, for predicting performance in distance events. When you combine RE with VO2 max and maybe lactate threshold, those three together can explain up to 90% of the difference in performance between runners.
Wow, 90%. That's huge.
It is. It means understanding RE is absolutely fundamental if you want to evaluate how people move efficiently and predict their endurance potential.
So it's not just a minor detail, it's core.
Absolutely core. Now, traditionally, the way we've tried to measure this indirectly is by looking at submaximal oxygen uptake, VO2 sub.
Right, I've seen that metric, milliliters per kilogram per minute.
That's the one. ml/kg-min. The idea is simple. Oxygen consumption should directly reflect energy use. More oxygen, more energy burned.
Seems logical.
It seems logical. But this method has faced some serious questions recently.
Okay, here's where it gets interesting. Why question VO2 sub? It feels so intuitive. Where's the catch?
Well, the study digs into this, and there are really two main issues that come up. First, there's something called the metabolic shift.
Metabolic shift, okay.
Yeah. Think about your body's fuel sources. At lower intensities, you tend to burn more fat. As you increase the intensity, you shift towards burning more carbohydrates.
Okay, fats and carbs, different fuels.
Exactly. Now here's the twist. Burning carbohydrates actually yields a bit less energy per liter of oxygen consumed compared to burning fat.
Wait, less energy per liter of oxygen for carbs?
Correct. So as you work harder and shift to using more carbs, your total energy expenditure might be going up significantly, but your oxygen consumption might not rise proportionally or might even plateau slightly.
Ah, so the VO2 measurement might not fully capture the actual increase in energy cost if you're switching fuel types.
Precisely. It can mask what's really happening metabolically, potentially giving you a misleading picture of your running economy, especially at higher submaximal intensities.
That's a definite aha moment. So the oxygen reading isn't the whole story.
Not necessarily the whole story, no. And the second big issue is something called ratio scaling.
Ratio scaling.
It's simply the standard practice of dividing the VO2 measurement by body weight, that ml per kilogram per minute.
Right, to compare people of different sizes. Seems standard.
It is standard, but it assumes a simple linear relationship between oxygen uptake and body weight. Double the weight, double the oxygen use. But biology is rarely that simple.
Okay. So it's not linear.
Often not. Previous studies, particularly looking at VO2 max, found a nonlinear relationship. Using simple ratio scaling, where you're essentially assuming body weight has an exponent of 1, can actually underestimate someone's true aerobic capacity while potentially overestimating their running economy.
So just dividing by weight could be, well, it's statistically flawed. It might make heavier people look less economical than they are, or lighter people more.
It can introduce a bias, yes, leading to inaccurate comparisons between individuals. It's a subtle but potentially significant statistical artifact.
Okay, so those are some serious concerns about the standard VO2 sub method.
They are, and that's exactly why this study set out to investigate. They wanted to compare this traditional ratio-scaled VO2 sub against a more direct measure, energy cost, or EAT.
Energy cost, measured how?
Calculated in kilocalories per minute, usually derived from both oxygen uptake and carbon dioxide output, which helps account for that fuel source issue.
Ah, okay. More direct energy calculation.
Yes, and their hypothesis was that EAC, especially when scaled properly, using something called allometric scaling, would be a more appropriate and accurate measure of RE.
Allometric scaling, we'll need to unpack that too. But first, who did they study? Elites, or more everyday runners?
That's an important point. They studied 69 recreationally active college students, aged 18 to 30, regular running habits, so definitely amateur runners.
Okay, so relatable to a lot of listeners, not super elite athletes.
Exactly. Which makes the findings potentially more broadly applicable. They did a range of tests, VO2 max tests, running at different submaximal intensities, 55%, 65%, and 75% of their VO2 max.
Oh, yeah.
And also 8,000-meter running performance tests to see how RE related to actual performance.
Comprehensive. So what did they find? Did VO2 sub hold up at all for these amateurs?
Interestingly, yes, to some extent. Contrary to some earlier studies that saw a bigger disconnect, in this group, both VO2 sub and the energy costs, EBER2, did significantly increase as the running intensity went up from 55% to 75%.
Okay.
So this suggests that for these recreational runners, VO2 sub can still be a valid indirect measure. It does reflect changes in metabolic demand within an individual.
That's sort of good news then. VO2 sub isn't totally useless for casual runners.
It seems not totally useless, no. But this is the crucial part. How you scale it still matters immensely.
Back to the scaling issue, ratio versus allometric.
Exactly. This was perhaps the study's most significant finding regarding how we compare people. Allometric scaling was far superior to ratio scaling.
How so?
When they used allometric scaling, the influence of body weight on the RE measures basically disappeared. It properly accounted for body size differences. But when they used the traditional ratio scaling just dividing by weight, they often found significant negative correlations between RE and body weight.
Meaning heavier people looked less economical just because of the math, not necessarily because they were truly less efficient.
Precisely. It confirmed that ratio scaling introduces that bias. Allometric scaling removes it.
Okay, I need to understand this allometric scaling better. How does it actually work? And they mentioned a 23 law.
Right. So allometric scaling acknowledges that biological variables often don't scale linearly with size. Think about surface area versus volume. Instead of just dividing yx, allometry uses a power law relationship, like y times x raised to the power of b. Here, y is the physiological measure like VO2 or EC, x is body weight, and b is the crucial scaling exponent.
So b isn't just 1, like in ratio scaling.
Correct. The study actually calculated the b exponent from their data, and it consistently clustered somewhere between about 0.43 and 0.81 across the different measures and intensities.
And how does the 23 law fit in?
Well, that range nicely brackets the historical 23 law. This principle, which actually dates back to the 1830s, suggests that metabolic rate scales with body weight raised to the power of roughly 2/3, or 0.67.
Wow, that's an old biological principle?
It is, and it's supported by a lot of biological scaling theory. The study found their data aligned well with it, and they suggest that for practical purposes, just using the 23 exponent is an acceptable and much better approach than ratio scaling.
So instead of just dividing by weight, we should ideally be dividing by weight raised to the power of 2/3.
Essentially, yes. That provides a much more biologically sound way to compare running economy between people of different sizes.
That feels like a major shift. If coaches or apps are still using simple ratio scaling, they might be getting, as the study put it, faulty information.
That's the implication. It could lead to misleading training schedules or inaccurate comparisons.
Okay, so allometry is key for comparing people, but between VO2 sub and energy cost, EC, which one came out on top overall?
For the highest accuracy, especially in research settings, or if you need really precise individual assessment, the allometric scaled energy cost, EC, proved superior.
Why superior?
It just showed consistently higher accuracy in their statistical models. It was more sensitive in detecting those correlations with the actual 50-meter running performance.
Makes sense, as it's a more direct measure of energy.
Exactly. It bypasses those potential issues with fuel utilization that can affect VO2 sub alone. So ESIC, scaled allometrically, seems to be the gold standard if you need maximum precision.
Got it. Now, what about the intensity for testing? They tested at 55, 65, and 75% VO2 max. Did one intensity prove better for measuring RE?
Yes, that was another key finding.
Oh.
The correlations between running economy and actual running performance were strongest when RE was measured at the moderate intensity, 65% of VO2 max.
Interesting. Not the highest intensity.
No. At the higher intensity, 75% VO2 max, especially for the female participants, they started seeing signs that the runners weren't quite in a true steady state.
What kind of signs?
Things like elevated blood lactate levels, indicating more anaerobic contribution.
Right. And also a higher respiratory exchange ratio, or RER.
RER. Remind us what that shows.
Sure. RER is the ratio of carbon dioxide you breathe out to the oxygen you take in. A value around 0.7 suggests mostly fat burning, while closer to 1.0 means mostly carbohydrate burning.
So a higher RER at 75% means they were relying heavily on carbs and maybe pushing beyond a purely aerobic, steady effort.
Precisely. And that shift can compromise the sensitivity and accuracy of the RE measurement itself. You're not capturing that pure aerobic efficiency anymore.
So testing too hard might actually muddy the waters when you're trying to measure economy. The sweet spot seems to be that moderate 65% intensity.
That's what this study suggests, yes. Around 65% VO2 max seems optimal for capturing the most meaningful RE value in relation to performance.
Fascinating. Okay, one more really intriguing finding you mentioned earlier, differences between sexes.
Yes, this was quite notable. In this group of amateur runners, the females consistently showed better running economy than the males.
Better economy. So more efficient.
Yeah.
Yes, more efficient. And this held true whether they calculated RE using energy cost or VO2 sub, and whether they used ratio scaling or the more accurate allometric scaling.
That counters some common assumptions, or at least conflicting reports we sometimes hear.
It does. And the study makes a strong point here. They noted that when they applied the proper allometric scaling, these sex differences became extremely large.
Wow.
Their interpretation is that much of the inconsistency in previous research about sex differences in R might actually be due to those statistical defects of ratio scaling.
So the flawed math was hiding or confusing the real difference.
That's what they strongly suggest. Proper scaling reveals a clearer and perhaps surprising picture of female efficiency in this context. It implies that training benchmarks based on older ratio-scaled data might need reevaluation.
This whole study just turns so many assumptions on their head. It's been a really insightful deep dive.
It really challenges us to be more precise. So, to kind of summarize the key takeaways.
Yeah, let's recap.
For amateur runners, like the ones they studied, submaximal VO2 uptake, VO2 sub, can still be a valid way to track changes in running economy within yourself.
Okay, good to know.
But for maximum accuracy, especially if you're comparing between people who are doing research, energy cost EV is probably better.
The gold standard.
Right. And crucially, whichever measure you use, you really should be using allometric scaling, specifically applying that 23 law for body weight, not simple ratio scaling. That's key for reliable comparisons.
Makes sense. Proper math for proper biology. And test at that moderate intensity.
Seems so. Around 65% VO2 max looks like the sweet spot for getting the most meaningful and performance-related RE measurement.
Connecting this to the bigger picture, then, these findings aren't just academic tweaks. They provide a much more solid way to assess running economy.
Absolutely. It could lead to much more personalized and hopefully more effective training strategies down the line. Less guesswork based on potentially flawed comparisons.
So what this means for you, the listener, is maybe the next time you look at your running stats or think about improving, consider this efficiency piece. How efficiently are you really moving? And are you measuring it in a way that truly reflects your physiology? These new insights might unlock potential you didn't realize was there.
It opens up new ways to think about progress.
Definitely. Now, we've really just scratched the surface here, covering the highlights.
For sure. The methodology and detailed results are worth exploring.
So we strongly encourage you, if this piqued your interest, to read the full article. Again, it's Quantifying Running Economy in Amateur Runners, Evaluating VO2 and Energy Costs with Model-Based Normalization.
By Xiuli, Zhang, and Zhaowei.
In the Journal of Sports Science and Medicine, the 2025 volume. Definitely check it out for the nitty-gritty details.
Absolutely.
And if you found this deep dive valuable, please make sure you follow our channel, turn on those notifications.
Yeah, don't miss out.
So you won't miss more fascinating insights like this from the latest research.